Alrighty, this is part 3. We did ones that were primarily based upon triangles. It's amazing how many of them actually are based upon triangles, but there are other varieties of related rates, and I want to at least get to a few of those. Well, we're going to, of course, get to one right now. Let's go ahead and look at number 5 on that same worksheet that we've been working from. It says air is escaping from a spherical balloon at a rate of 2 centimeters cubed per minute. Okay, so that sounds like given information. Okay, and you can go ahead and draw yourself sphere if you want. I mean, it's what a sphere looks like, so it's really not incredibly necessary in this particular one, but just to stick with our game plan. Now, I know that if air is escaping, that is a change in volume, okay? And so dV dt is 2 centimeters cubed per minute, right? Wrong. It's negative 2 centimeters per minute. Got to be very careful about when the rate is causing something to diminish or to get smaller, you have to make it negative. So if air is escaping, it's negative. If air is being pumped into the balloon, of course, that would be positive. Now it says, how fast? Okay, so it's already started to ask the question right now. So that's pretty much guaranteeing that anything that comes after that is likely going to be conditional information. So it's going to ask the question right now, how fast is the surface area of the shrinking when the radius is 1 centimeter. So ds dt is equal to what? On the condition, okay, that r is equal to 1 centimeter. Okay, well, we got that? Now, the rest of this, v is equal to 4/3 pi r cubed and s is equal to 4 pi r squared, where v is the volume and s is the surface area and r is the radius. Here's the thing. At this point, you need to have rememorized all of your geometry formulas. So that should automatically be in your memory bank. So should that. Okay. Now it says it's asking for ds dt. Now I happen to know that volume being 4/3 pi r cubed and surface area being 4 pi r squared, that there happens to be a relationship between them. Okay. Now, if I want to deal with s, that's fine. But I could, if I wanted to, I could go ahead and rewrite this as volume is equal to r over 3 times 4 pi r squared. Okay, if I wanted to, and therefore substitute in, like take s and sort of plop it into there. You could do that. That still winds up giving you, that winds up taking it from 2 variables to 3 variables, okay? And I wouldn't do that if I were you. I would go from volume, and I wouldn't put volume in terms of surface area. I would basically differentiate both of them. dV dt is equal to 4 pi r squared dr dt. And ds dt is equal to 8 pi r dr dt. I would solve this one for dr dt and then use that information and plug it into here. And that way it winds up being a little bit easier than trying to deal with the product rule here. That's just not a good move, okay? Notice 4 pi r squared, 4 pi r squared. Okay, so you know that dV dt is negative 2 centimeters cubed per minute, and you know that this is 4 pi r squared dr dt. Well, that's 4 pi, because 1 squared is not really worth talking about. And therefore it becomes, but of course this is centimeters squared, so when you divide, you wind up getting -2 over 4 pi, or -1 over 2 pi centimeters per minute, and that is dr dt. Well, let's go ahead and bring this down right here, and I know that ds dt, I'm looking for that same moment in time, so this is still 1 centimeter, and I know that this can be dropped in for dr dt, so that's -1 over 2 pi centimeters per minute. The 8 pi and the 2 pi cancel out, and I'm left with -4 centimeters squared per minute, and that winds up being ds dt, the change in surface area. Okay, that winds up being just a little bit easier than trying to wrestle with. I don't even know if you could, but I'm just saying that just from the get-go you can see that that's just a bad idea to try to substitute in. Yeah. Okay, let's go ahead and move forward from there. That has to do, of course, just, I mean, it's the same principle, right? It's just a different equation or different set of equations that we've used, and but we've still done the same thing. We drew a picture. In this case, it wasn't really necessary because a sphere is just a sphere, right? We have the given information. We identified the question and the conditional information that that question is based upon. From there, we designated 2 equations instead of just 1. We used the volume to back into a value of dr dt so that we could then use dr dt, which was necessary in order to get our answer for ds dt. Okay? Now, you're obviously going to have to ask your teacher as to whether she wants you to put your answer in complete sentences. You know my preference on that. And I forget whether it's necessary on the AP exam. But, okay, so we've done 5. Let's go ahead and move on to another one that is not right triangle related. Okay. A block of ice in the shape of a right circular cone. Oh gosh, no, I wanted a block of ice that wasn't in terms of a... No, it's still another one. Okay, let's deal with this one. Sorry, I'm going to call an audible real quick. Okay, number 7. This is a different worksheet. Oil spilling from a ruptured tanker, okay, spreads in a circle on the surface of the ocean. The radius of the spill increases at a rate of 2 meters per minute. How fast is the area of the spill increasing when the radius is 13 meters? Well, you know, and the thing is that you actually could do this not just in terms of a circle, but you could actually talk about the, how the thickness of the spill and actually do it in terms of a cylinder as well. I've actually seen that. But this one actually should be relatively straightforward since it's just a circle. Okay, I know that it's going to be increasing, right? Okay, so the radius of the spill increases at a rate of 2 meters per minute. Okay, so that's part of your given. That is dr dt is equal to +2 meters per minute. Okay. Now, it says how fast is the area increasing? So that's asking for dA dt when, and here comes your conditional information, when r is equal to 13 meters. Okay. Well, this one, like I said, ought to be very, very easy. A is equal to pi r squared becomes dA dt is equal to 2 pi r dr dt. I'm looking for dA dt. I have a constant, a given value for dr dt, and I have a conditional value for r. And so it's just a matter of plugging in. 2 pi times 13 meters times 2 meters per minute. And that's going to give us an area that increases at 2 times 2 is 4 times 13 is 52. 52 pi meters squared per minute. And that is the rate at which the area is increasing at that particular moment in time. Okay. Now, you can actually do this in reverse. Okay, and here's an example. Water slowly evaporates from a circular shaped puddle. The radius of the puddle decreases at a rate of 8 inches per hour. Assume the puddle retains its circular shape. At what rate is the area of the puddle changing when the radius is 3 inches? That would basically just be the oil spill one that we did in reverse. Okay, you are given the fact that the radius dr dt decreases, so this time it's negative inches per hour, and that sounds really slow, but you know, evaporation happens slowly. And it says, assuming the puddle retains its circular shape, what is the rate of the change of area of the puddle when, and here comes your conditional, right, when the radius is 3. And it is exactly the same thing. A is equal to pi r squared becomes dA dt is equal to 2 pi r dr dt. 2 pi times 3 inches and then negative 8 inches per hour. That winds up being 2 times 3, which is 6, times negative 8, which is negative 48. That's negative 48 pi inches squared per hour. And that is the rate at which it decreases. Same exact thing, just in the opposite direction. Okay? Now, tell you what, I'm going to go ahead and end this video because the next one that I want to do is a classic, but it actually winds up taking a bit of time. And so we're not going to get to it in the usual, we're not going to be able to finish the video in the normal 15 minutes that I try to keep us down to. Yeah, we'll go ahead and do that on the next video, so be looking for that.